First of all, I'd like to thank the organizing committee for invitation, and it's a great honor to speak in this conference. So I'm going to speak about RTL classes and just some simple observations. I will start with just classical RTL class, and which you have seen in Damien Clark's lecture already, but I'm going to repeat again. And then basically the plan is to speak two generalization of RTL classes in two different contexts. One is over the Lie algebroids, and which just in a few minutes will be clear what context is. And the second is for vector bundle over a stacks or holomorphic in case, or even smooth. And what is RTL class? So those are the somehow very natural question, and it might be written somewhere, but we just couldn't find it. And so I thought it's interesting to point that out. But it's just very simple observations. All right, so let me start with the RTL class. And you have seen this in Damien's talk already. X is a complex manifold. And E is a holomorphic vector bundle. If you take J1 E, and this is the first jet, bundle of the first jet, of sections, I mean sections, holomorphic sections, of course, in this context of E. And then you will have this exact sequence. I'll write this in the form of the bundle. And therefore, the extension class is the RTL class. So here I'm just changing this to omega 1. And this guy is so what the RTL class measures is exactly if this class is 0. This measures that means you can split. You can split this. You can have a section. So this just says you can have sections. This just says connection exists, holomorphic connection exists. So exactly this measures the existence of a connection, holomorphic connections. And I think this first was due to RTL around 1957. I'm not quite sure if this is a context RTL introduced or maybe principal bundle. Well, it is exactly the same. But more recently, people got interested in RTL classes. And for more recent, around 1999, I think Conceivage and later on, I think around the same time, Kapanov. Basically, in the study of Lozenski-Witter invariants. and they come up a conceptual way of studying this Lorentz-Witten invariance, which is a three-dimensional invariance of three-dimensional three manifolds. And so the paper, which having very a lot of influence or interest is this paper by Kapanov. Invariance by Atiyah class, which probably Damien also mentioned about it. Another paper which is important in the subject, at least for our interest, is a paper around 2005 by Makarin. I don't know how to say his name. And later on, Lamados. And this is extremely, so this paper is on archive. And it's Atiyah class, Huxley homology, and Riemann-Lach theorem. So basically, they will come up a new proof of Riemann-Lach theorem. Probably this, and also some other, as you already see in Damien's talk, this Atiyah class appears very naturally in the study of Huxley homology and Huxley constant Luxemburg theorems in Clark and Vanderbient's work. So for us, basically, these two, especially this one, is we try to understand this basically what really makes this works. And let me just start with come back to this one and rewrite this Atiyah class in a Debye coordinate, Debye resolution. So let's look at this class in Debye models. It's very standard and very simple. Now you pick up, you probably have, I think Damien talked about this also. Pick up any smooth connection on E of 1,0 type, namely this equivalent derivative having the usual connection property. And I just that out to be commutator to this d bar operator. And this in fact, just another way of thinking of this is just you want a partial bar plus 1, 0 is connection, and this is just curvature, 1 part curvature. Or you can just take commutator. So this guy defines basically its covariant derivative is just 1, 1 tensor. And you can see, in fact, this is just curvature. So this is just a section. This is just a section induced. A section, so induced by 1, 1 tensor anamorphism E. You can see this is a tensorial. And then the class of this is exactly the Atiyah class. And this guy is the cohomology. Now, this sheaf cohomology of X omega 1 tensor anamorphism E is using the Dubois solution. So here, probably let me record this because I'm going to use this later on, and you can compare it. And this guy is a sheaf cohomology over the X, but you use the Dubois solution. Namely, this is just cohomology, first cohomology of this complex over here. And I think I did something wrong. What is wrong here? This is 1, 0. Thanks. And this should be 1, 2, right? So that's the coaching complex I'm using over here. All right. So this is very classical result. And now I want to move to the 2, and just let me talk about one simple observation, which is almost trivial, is the following fact. A smooth vector bundle so this is just for the motivation. And a smooth vector bundle, X is a complex manifold. X is a complex manifold. So a smooth vector bundle is holomorphic if and only if you can consider this. There's a connection of T01 connection over E, which basically tells you the holomorphic direction, which is flat. In other words, this is a T01 module. So E is T01, and when I write this, it really means T01X, a module. And basically, you want to think there's a module just means to have a connection over here. So, and what is a T01? X, and if I write this A, and this is just Lie algebroid. So this guy is a Lie algebroid. Oops. And so another way to rephrase a tier class is exactly just what is a tier class is exactly just obstruction class for the existence of, in some sense, because you want a holomorphic connection, basically take a covariant derivative, well, you want a holomorphic connection on E. So you want some compatible connection, well, of T10 on E. So holomorphic connection, basically you can consider a smooth connection, a connection of T10 X, which is just smooth connection. Here I'm just seeing complex vector bundle, just smooth connection, which is compatible in the sense if we're taking somehow the flat over the first T01, and then you take covariant derivative with flat over here, it's still flat. So I'm getting to it, what this means. So, and if I call this the B, again, B is another Lie algebroid. That's very clear. That's another Lie algebroid. And so if you look at A plus B, is just Tx complexified cotangent bundle, tangent bundle, which is another Lie algebroid. So this is a constitute what is called matching pair in Marcus' lectures. I'm here, so let me just recall what is a matching pair. So this is exactly what is a matching pair is. And so a pair of Lie algebroid AB is a matching pair if A plus B is a Lie algebroid, and A plus 0, and both A plus 0 and 0 plus B are subalgebroid. Well, in particular, if such things exist, automatically B is A module namely A acts on B with flat connections, with A flat A connection, and A is B module. In fact, the matching pair can be described by this two pair of A-B module and then with some compatible conditions. And let me just give you a few examples what are matching pair. We have seen quite a lot of examples. So I think I was lucky that Marco gave a lecture before me, so he already showed you so many matching pair. So I don't have to convince you matching pair does appear very naturally in Poisson geometry. But here, nevertheless, I have a few more basic examples, somehow close to trivial examples. Let me see what the matching pairs are. And the first one, again, the standard one. If X is a compact manifold, and A is just T01X, and B is T10X. Those are matching pair. Another is a little bit variation of this example is, say, K, if K holomorphically algebraic, namely just the algebraic, everything just in holomorphic. You have seen holomorphic Coulomb algebra already, so this is much easier than holomorphic Coulomb algebra. So, and then A is T01X, and B is K10. Namely, whenever you have holomorphically algebraic, you can always have underlying smoothly algebraic, and then you extend it, will complexify and take the 10. It's just a very standard way. And this, again, a matching pair. And in the real geometry, matching pair also appears very naturally. For instance, X is just a manifold with transversal foliations. And then obviously this distribution corresponding to these two foliation are matching pairs. And now my last example, I got to say something related to Poisson. And in fact, this is the first, this is how I learned the matching pair. And this beautiful examples due to Jianhua Lu, and this is the first I learned this matching pair of Lie algebra actually, is you getting G is a Poisson group. And if P is a Poisson space, Poisson G space, namely it's Poisson manifold, this map, the action map, is a Poisson map. And then you can take A to be cotangent boundary of P with a standard Lie algebroid coming from the Poisson structure. And so just saying this example is loose. And B is the transformation Lie algebra of G. And G acts on P, so you have a transformation here. And this is a matching pair. And then you can play around this example by looking at very special cases. So you can cook up quite a lot of matching pair, which are related to Poisson geometries. All right. So now, what do I mean by a tier class compatible AB? So my setup, let me just the setup over here is following the general setup. Here, AB is just a matching pair, matched pair of Lie algebra. If you have, it's used for just to keep the example, the first example in mind, that everything's more or less kind of trivial. So if AB matched pair of Lie algebra, and E is a vector bundle, which is A module. And that's the general setup I would require. And now you say a B connection, so this is a small a, let's say. A B connection E is compatible with A module structure if just the flatness condition holds, namely AB is A covariant derivative B. And this acts on, this is just the gamma E to gamma E. And here A is section of A, and B is section of B. And here, this is basically just the flatness, partial flatness. Here AB bracket, because I assume matching pair. So if I have matching pair, you can take a bracket. And then you can have on A plus B. And then still you have A part and B part. So why this? Why this is a flat? Yes?
So A bracket B is in A plus B. So which connection will we use?
Here, so on the left-hand side, I'm using here just a simple notation. On A plus B, you have a bracket here because matching pair. So this guy, and then you will split on two terms over here. And then the covariant derivative on A part will be just the module structure. And then B is the connection. So I just, yeah, that's the meaning. So why this? I just try to justify. Well, that's the simple way is just exactly if O is just the sheaf of A flat functions. On X. Namely, those are the function f and similarly you can have BA, and those are sheaf of A flat section of a B, and also EA, and those are the sheaf of A flat section of E. And now it's very easy to see if so I'm putting a smooth, and that means it's just smooth section. Sheaf of smooth section is spanned by you really think of this as just the holomorphic sections. And this is B. And this is C for smooth section. And then the existence. So exactly what the compatible connection is the same as a B connection, this connection and a B connection. E. Okay, this is almost trivial to see. It just means, like this is a sheaf, and you take a connection on this sheaf, so this preserve. B exists. Sorry. Exists. So basic existence of this flat connection compatible with flat connections. But nevertheless, even this condition fails. This compatible connection is interesting. I'm going to show you later on. And this obstruction class, which you may want to call Atia class, is really interesting. And so now, what is the obstruction class? So come back to the compatible connection. The obstruction class is very simple to write down. What is the obstruction class? All right, so now what you do is you just take any smooth connection, which already exists, any smooth B connection, on E, say lambda B, and it just imitated what I wrote down for the equation over there for the complex case. So R is the commutator of covariant derivative of A. Remember, we assume we have A module and B here. So, and this, one can check. This is just the curvature again. So this guy, in fact, defines a section of A star, tensor B star, and morphism E. It's a very simple fact to check. And now this guy is A module, because here we assume B is the A module and E is A module. So the whole thing is just A module. And you can check, this is obvious and very simple to check. This is a cocycle with respect to the Lie algebra differential A, and therefore define a class. This is the obstruction class. So the first theorem is kind of almost trivial, simple observation is this class is first Lie algebraic cohomology of A with coefficients in B star and the morphism of E is independent of a choice of a connection. And this is 0 if and only if compatible connection exists. So that's obvious. All right, so before I go on, let me just show you a few examples what this generalized. So this is what we call RTL class. It's obviously you want to call this RTL class again, right? And let me just show some examples, and you can see even in Poisson geometry we have seen this class already. So let me start just classical one again. And if you have the A is just T01 X and B is T10 X and E, I want A module and then just a holomorphic vector bundle. And this is a usual RT class. And a little bit variation of this example is almost similar to this, is you want to start with a holomorphic Lie algebraic. And now, obviously, this is A is, I take A is a T01 X, and B is K10, and the E is again holomorphic vector bundle, and then this RTL class is just the first Lie algebra cohomology of T01 X as Lie algebraic with coefficients at 10 star, K, and the morphism E. So this is just same thing, the first sheaf homology with K star and the morphism E. And this is exactly what people call the RTL class of a holomorphic vector bundle, holomorphic Lie algebraic. Holomorphic Lie algebraic on E. So this is the somehow standard RTL class. Now, another simple example is, let's start with A is any Lie algebraic. This is just smooth category, smooth Lie algebraic. For instance, A is cotangent bundle of Poisson manifold with the standard Lie algebraic. And B is a line bundle, which is a QA star. Due of this line bundle, QA is this Evans-Lou-Weinstein module. So let me just write down. I will write down the line bundle. What is the line bundle? So A tensor top degree of T star what is it, T star P. So as the line bundle is this one, but there's a module structure, which is the Evans-Lewontin module. And you take the dual, so obviously this guy is A module, and now, so this is the A module, and you put in 0 Lie algebraic structure. You let everything 0 over there. And now, obviously, AB is a matching pair. So AB is a matching pair. This. And now I take E to be trivial bundle. Well, this guy is the A module with A module structure. It's A module, and basically by action, by the anchor map of A. So this is the section of here are just the function. So this is obviously is A module. And now you can see what is a B connection. What is a B connection? So a B connection on E is exactly just nothing. It's just a section of the dual bundle of B star. So just a section which is the section of QA. And now you can guess what the RTL class is. And then it's so obviously you can expect the RTL class. Now the Lie algebraic cohomology with the module B star and the morphism of E. And this is just the Lie algebraic cohomology. The coefficients is just QA. And this is just module class. So you can realize module class of Lie algebraic is just a special case of RTL class. And well, now let me just further move to property of RTL class. And it turns out many of those properties RTL class, which is standard RTL class, property of RTL class, proved by Kapanov, can be just carried over in this context. And in particular, let me just point out. Where? No, I'm saying a B connection on E are equivalent to sections. All the sections. It's equivalent. So a B connection, just B is just line bundle on E is the same thing as point out just a section of a dual bundle. And now I want this connection to be compatible with A connection, namely I want this. So B star is QA, namely it's just exactly want the section to be compatible with A action, and that is just the module class that measures the mod. Is it okay?
I think you just wondering what if you choose alpha to 0?
What this? Yeah, but when choose oh, let me see. You're right. Is that it? Is that the connection? Can I look? Well, yeah. Well, Well, I have to think a little bit. Yeah. Well, let me go on and come back maybe later on. All right. So now, especially want to look at the special case is this E is just B itself, which automatically has a module structure. So if I take B take E to be B, and now alpha B, the module class, is the first Lie algebra cohomology A with the coefficient of B star and the morphism of B. And this is just B star tensor B. And which is given, as I say, this class is given by this guy is given by curvature, some kind of partial curvature, R. And now one can easily see this curvature is B1, B2. As I said, this is a section just given by the curvature. So R is A star tensor, this guy over here. So, and those are the components. So one can easily see if you switch B1 to B2, two argument, and this is a coboundary of dA and the torsion class. Torsion of the connection of B. So therefore, it's automatically, this guy is symmetric. So in fact, is symmetric. So it's very simple computation. So as I said, many properties of a usual RT class can be verified in this context without any modification. I'd like to just point out just a couple and skip all the rest. And one thing which I want to point out here is you do get a, let's say D is a module with compatible commutative multiplication and then the Lie algebra cohomology with a coefficient. Now again, B is I always assume my starting up as an AB matching pair. So A, D is a module, and now you can take a cup product because this is algebra. So this is the all A module. So and then you can cup with the RTL class, which is symmetric with the two components over here. So you couple with alpha b over here, and here you take the multiplication, and then you will end up right here. Oh, sorry, this is the no. Okay. So you end up hi plus j minus 1, a, and b, so d. And this is, in fact, this graded Lie algebra. And well, whenever you have graded Lie algebra, you may want to ask if there's an infinite structure there. And that's another thing I want to point out. The second theorem, in fact, there's an infinite structure underlying over here too. And so if assume lambda b, now I start with on the quotient level. So this is the cohomology level, and I want to look at the quotient level. So assume lambda b is torsion free. And flat, which in this case, there are two cases. One is a case actually in the case of interesting case in the Kapanov case, or the Lozinski-Witten invariant case, is just the B is, for instance, let me just show two cases. So if B is T10 and X is Kähler manifold. And A is just 0, 1. And just Levi-Theta connection will be flat connection, will be T10 connection, which is torsion free and flat. In fact, another situation by talking to Alan, just point out is if I have X is in the Liouville case, this happens in Liouville case too. If X is just symplectic manifold with transversal polarization, namely Lagrangian foliation, and F1, F2, and now you take A is the dF1, B is dF2, the distribution, and you do get there is flat connection, torsion-free connection over there. So in fact, one can really consider this case is kind of a complex polarizations, transversal complex polarizations. Really can be that situation too. So nevertheless, if you have this context, one can construct an infinite algebra actually, where it just follows exactly the same argument. You know, so on the L, so let me just, how many minutes I have? Less than 5. I think I'll just try to wrap up quickly. So G So those are the graded vector space. And now B1 is just covariant, just dA. I should say just dA, just Lie algebra differential. B2 is B2 is just G I think here plus minus sign, not careful. Omega wedge omega 2 and R2. R, I'm putting R here. And R is the curvature, which I defined over here. The curve R is just the representative over here. This is R here. So this is Y1, Y2. And so those are the A part, and this is the B part. And you can cook up a similar formula, use Rn, and basically, and Bn. And now the only thing is Rn is defined to be Rn minus 1, and which is a section of A star tensor B star So here you have our 2. I think this will have n factors here. So by keeping just induction covariant derivative here. And we'll be using the same formula. You have n terms and plus sign. So and the theorem, using this, you can define a Bn. And the theorem is, and this is infinite, is infinite algebra. Well, let me try to finish by making some comments. Actually, the direction we try to, this is like work in progress. And in fact, one direction which we are interested in to figure out is just a very special case of if A is just T01x and B is just K10, and the K is a holomorphic Lie algebroid. And in fact, the question here, it was in the case of Kapanov, if this K is just Tx10, and what the Kapanov shows is this L infinite structure is exactly the infinite is the nonlinear. So what is in the case if somehow this infinite structure, which I described, is gave you a new holomorphic structure on the tangent bundle, zero section tangent bundle, such that this is so-called holomorphic exponential map. So you pull back, so there's a so-called holomorphic exponential map. The usual map is not holomorphic anymore. So this is, I think, due to Calabi in 50s, and later on, so physicists discovered later on there's a holomorphic exponential map, which is not in the usual case because you don't have Holomorphic connection anymore. So exactly what it shows, this infinite structure is a new, somehow it's a new holomorphic structure on this, which is pulled back by this exponential map. So one question, which is very natural in this case, in this infinite structure, should give you somehow the holomorphic exponential map from the holomorphic Lie algebra to the holomorphic Lie groupoid. So this is a question would be interesting. Is there any holomorphic exponential map from a holomorphic Lie algebra to its underlying holomorphic groupoid, which the exponential map, which really is governed by this exponential map, by this infinite structure there. And the second thing I want to say over here, I'll try to avoid it because I don't really fully understand, is as I say, the motivation for Karpanov is try to understand this Lorentz-Witte invariance. And what this invariance is, basically, what they show is you can cook up this, basically, given by some weight, and those can be defined by a holomorphic symplectic manifold. The holomorphic structure and gives you the Atiyah class, which is actually Lie. It's Lie. Well, in the sense you have to go to derived category of coherent sheaf, whatever. Then this gave you tangent, just like in Damien's talk. Is a Lie function. Atiyah class is defined the Lie function over there, and the symplectic structure gave you a metric on this Lie algebra. So in other words, you get a kind of quadratic algebra. A quadratic algebra in this somehow derived category, which I don't want to get into it. So now you can see it's very parallel over here. What I have shown you, in fact, I try to avoid this language, which is actually true, is I'm giving a matching pair, A, B. And you do have a Lie algebra in this category of, now you should look at A module, the derived category of A modules. And you do have a Lie algebra structure there. So the next thing probably one might be interesting to see is what is the other quadratics, which is pairings there, and see and how whether this gives rise to any new invariance or not. Basically, that's all the data you need. So that's another interesting direction, I would say, to what we're interested in at this moment. But I think I have no time to touch this. But those are more or less obvious. I will stop here. Thanks.